the tertiary consists of a dark gray clay layer, and there the life had almost disappeared. And the KT boundary is just in between. I can point at it. It's right here where you see a contrast between the purple and the dark. It's an extremely sharp boundary.
And just across that thin little boundary, there's this huge change in what you see in the forams. And why is that so stunning to you?
It's so stunning because there is no preceding evidence of anything happening there. So it doesn't matter if I take a piece here, a piece there, or just underneath what we call the KT boundary. The foraminifera will remain the same, so they don't change overnight. And then, bang, they're gone. So what's that telling you? That tells me the base of the food chain of the oceans disappeared. And everything which is dependent on it is totally zapped right at the boundary.
In Amsterdam, change at the boundary becomes clearer when Smit takes a closer look at the evidence. In his lab, he analyzes forams extracted from the limestone. Under the microscope, the rich diversity of fossilized shells from the Cretaceous snaps into focus. Some 4 dozen species appear below the boundary. But above it, there's a different world.
These are the foraminifera from just below the boundary. And these are from just above the boundary.
Only a few species have survived into the tertiary, and they're much smaller.
As soon as you see that extinction and you realize at the same time that the dinosaurs are disappearing, you know you're looking at something very important. But you see,
Okay, so what is the KT boundary? The KT boundary is the end of the Cretaceous time period and the beginning of the Tertiary. In the rock layers, the KT boundary is at the bottom of a clay layer. What are the differences between the foram between below and above the KT boundary? You just said it, the diversity of foram fossils of the Cretaceous layer is the same regardless of age. But then there's a sudden decline in the biodiversity at the KT boundary, suggesting that the base of the ocean food chain disappeared. Below the boundary, foram species are bigger, above the boundary is smaller. There are fewer species in the tertiary.
but he has witnessed it. So we're looking for silent witnesses in the rock, and the first thing that comes to mind is this beautiful clay layer.
A layer varying in color and thickness and found around the world. Walter Alvarez also believed it was a silent witness to the end of an era. The key question was, how long did it take to form, for the world to change? To find out, he sought help at the University of California at Berkeley from a Nobel Prize winning physicist. Someone he knew pretty well, his father, Louis Alvarez. Louis loved a good mystery, no matter what field it was in. And that's how physics joined geology in the quest to explain the KT extinction.
Alvarez looked at this layer, tried to figure out how he could determine the time scale. He brought in his knowledge of astrophysics, his knowledge of nuclear physics, and realized that there's an element that's relatively rare in the crust of the Earth that occurs in meteorites.
The element was iridium, which falls steadily in an invisible rain of cosmic space dust. If the layer had taken thousands of years to form, Alvarez thought there might be just enough iridium to measure. But when the clay was tested, scientists were stunned to find it contained 30 times more iridium than the surrounding rock. Moreover, samples from other KT sites had similar levels, too much to come from ordinary space dust. What could explain so much iridium deposited around the world? Perhaps a catastrophic event in outer space. Alvarez wondered if a supernova exploding nearby might be responsible.
So he asked me if that was possible. And I concluded that there was only one chance in a billion that such a supernova would occur that close in 100 million years.
A supernova would have also deposited a rare isotope, plutonium-244. But testing revealed there wasn't any.
Well, I suggested alternatively that it could have been an asteroid or a comet.
There are hundreds of asteroids whose paths cross the Earth's orbit. Their sizes range from a few meters to hundreds of kilometers across.
So Luis Alvarez had this hypothesis that an asteroid or comet would cause this destruction. He had the clue, the amount of iridium at Gubbio. Under this hypothesis, it would be spread all around the world. So now he could calculate how much iridium there had been laid down over the entire Earth. Now, he also knew how much iridium there is in asteroids and comets, so he can now calculate the size of the object.
The answer was sobering. An asteroid 10 kilometers in diameter, as large as Mount Everest, and weighing hundreds of billions of tons. Still, how could something that size wreak havoc on a large planet? Because traveling through the vacuum of space, it would have slammed into the Earth's atmosphere at 80,000 kilometers per hour, 20 times faster than a bullet, heating the air to several times the temperature of the sun. At impact, the energy released would be equal to about 100 million nuclear bombs exploding at once. A huge mass of pulverized debris would have been blasted into space, some of it orbiting the Earth before raining back down. The debris may have blocked out the sun for months. Photosynthesis would have stopped. Plants, plant eaters, and then meat eaters would have died. This was the asteroid impact hypothesis for how the Mesozoic era ended. A big idea that was just too big for some.
When the Alvarez hypothesis was first proposed, it was difficult for many scientists to accept, because for almost 2 centuries, geologists had crafted their worldview around a gradual picture of slow but steady change in the Earth without major catastrophes. Now they're hearing a proposal that something had come from outer space and rewritten the history of life in almost an instant.
Luis Alvarez got very frustrated when the paleontologists didn't say, "Yes, sir, thank you for solving our problem." But many of the paleontologists just looked on him as someone who didn't know their field and was stepping into this just because it was such a big, important, famous problem.
The controversy would continue for years. To convince the skeptics, more evidence was needed. One criticism of the KT hypothesis was the lack of a crater the right age, type, and size. Alvarez thought it should be 200 kilometers across, bigger than the state of Connecticut. How could you miss that?
Well, one of the questions too is, what evidence did Luis Alvarez use to propose this hypothesis that an asteroid hit the Earth 65 million years ago? That is the element of iridium, and it's fairly rare in most Earth crust, but it's found in neutrons. The clay layer contains 30% more iridium than the surrounding rock.
They looked for craters that was 65 million years old all over the Earth. Many of these things had been discovered and had been measured. Didn't find any.
2/3 of the planet is covered by water. If the asteroid landed in the ocean, the crater might never be found. Even so, there would still be a trail of debris, ejected, blasted from the crater. So attention focused on finding this evidence. Geologist Jan Smit discovered glass-like beads in KT boundaries called spherules, formed when vaporized rock cools and rains back down. Another key clue was rock that had been so shocked by the impact it had crisscrossing bands of dislocated minerals. This was shock quartz.
And we know if you set off a nuclear bomb, the damage done to the surrounding rocks will produce you a shock quartz. So if you put two and two together, we find shock quartz at the KT boundary and shock quartz in nuclear craters. You know it is an explosion which deforms your quartz crystals. And quartz is only found on land. So that was the big clue. We have to look for a crater somewhere on land.
The search for fresh clues led here to Texas, along the Brazos River, some 300 kilometers from the Gulf of Mexico. 65 million years ago, this was the bottom of the sea,